Hi everyone. This is the second video for alcohol's properties. So we already saw some of the reactions that can make alcohols, and one of the reactions, very common combustion reactions, alcohols can do this as well, just like alkanes and alkenes. Now we're going to see some more types of reactions that alcohols can do. This first one here is quite important because we can see, if we use a colorful reagent, we can see this oxidation reaction. Now you've done lots of oxidation in Unit 6 and we're seeing it here again. And we can also see the difference between primary, secondary, and tertiary alcohols. So how about I start with a primary alcohol example and see what happens. Okay, the two most common reagents, and it doesn't matter which one, they work very similarly, are potassium permanganate, permanganate in acid, because it has a purple color. And when it reacts, it becomes colorless. Also dichromate, again, because it has a color. This one's orange, but when it reacts, it becomes green in color. So I've just chosen permanganate there, just random. And so what oxidation, the opposite of reduction, we saw reduction in the last video. And so this is going to lose hydrogens or gain oxygens. But in this one, it loses 2 hydrogens around that oxygen, and we end up with an aldehyde and a double bond. So it's almost like elimination as well. But the interesting thing with this primary alcohol making an aldehyde, then the aldehyde can react again. This time it can't lose 2 hydrogens around the aldehyde group because there's only 1 hydrogen. There's nothing on the oxygen already, but it can gain an oxygen. And this is an acid group that we saw before when we learned about weak acids, that's COOH. And we'll learn a whole section about these as well. So what about secondary alcohols? It's a little bit different. So at the first, well, for the reaction, just like with primary alcohols, there's these 2 hydrogens here, and it can lose those 2 hydrogens and make a double bond. But the difference is it can't react again. So this is a ketone. A ketone cannot be oxidized because it doesn't have this hydrogen here that the aldehyde had that could become an OH. Ketone doesn't have that on the C double bond O group. What about tertiary? Well, this one, there's our hydrogen that we would normally lose, but there's no hydrogen on the carbon. That's a tertiary alcohol. That's what it does. That's what makes it a tertiary alcohol. So it can't react. So we can see the difference between a primary and secondary. Those are the same. They can both react, although they do make slightly different product. We couldn't see that. But a tertiary alcohol can't react, so there'll be no change. And so just to remind you, just to put it in writing, the color changes. The potassium permanganate, you should know, hopefully you remember that it's purple, and it becomes colorless when it reacts in acid. The dichromate is orange, and when it reacts, it becomes green or sometimes even blue, like kind of a gray-blue color. And so you might see, that's why you might see different colors in different descriptions. So we can see the change. So this oxidation reaction is a very useful one. We can use it for identifying. So we'll do a whole section about distinguishing and identifying which kind of compound do we have. So this one will be useful in that section as well. All right, so there are 2 more main types of reactions that alcohols do. Well, 3, but won't talk about one much. The next one, substitution. It's substitution to add a Cl, so alcohol to chloroalkane. And again, there are many reagents. Probably the most important one is the Lucas reagent. Lucas reagent is made of concentrated hydrochloric acid and zinc chloride mixed together. But also we can use this reagent with sulfur and oxygen and 2 chlorines. Also, PCl5, do you remember seeing PCl5 in Unit 1 for the special shape that it has? And PCl3, phosphorus, can also have 3 chlorines or 5 chlorines. These last ones are very strong, and so we're actually going to see them again later. They're very good at adding a chlorine to other things as well. This one is not so strong, but actually that's very useful for alcohols because the Lucas reagent will react a little bit differently if it's primary, secondary, or tertiary alcohols. It can react with all three, so it's not the same as the oxidation here where we saw that it couldn't react, but it does react a little bit differently, and so we can see the difference. So we've got ethanol, good example of a primary alcohol. And for Lucas reagent, you can write Lucas reagent or you can write the chemical formula. So it's pretty simple substitution, just like we saw before. The alcohol group is substituted, replaced with a chlorine. What would we see? Alcohol is colorless. Haloalkane is colorless as well. So there's not a color change, but alcohol is soluble. Haloalkane is insoluble. So if we have a test tube, we would see two layers. See an oily layer coming up usually to the top, even though they're both colorless. But you can see that if you've got oil on water when you're cooking, you can see the oil on the water, even though it's basically colorless. Now I said they react differently. How do they react differently? A primary alcohol actually reacts really poorly. So normally we say no reaction is seen for a primary alcohol because it's so slow. We'd have to wait maybe 1 hour or 2 hours. So secondary alcohol reacts a bit faster, but it still takes about 10 minutes. Tertiary alcohol reacts fastest, say within about 2 minutes, usually, approximately. So we can see the difference if we notice the time that it takes for the two layers to form. So this one also is useful for distinguishing, for seeing the difference. The elimination reaction we can't actually see, but it's an interesting type of reaction, and we might want an alkene. Elimination reactions always make an alkene. And we saw this before with haloalkanes. Haloalkanes can do this as well. The reagent is different though. So I've written a triangle here. That's one way of indicating that it needs to be heated. And actually I used this abbreviation earlier, didn't I? And that CONC is short for concentrated or high concentration. So there's the reagent. That's the only one this time, not more than one to remember. And with elimination reaction, just like we saw before, it takes the functional group. We saw with haloalkane, so it would take the alcohol here and the hydrogen from one side or the hydrogen from the other side. But it always takes the functional group, but it can take the hydrogen from one side or from the other side, so we get two products. And when the two sides are different like this, just like with addition, when the two sides are different, one is easier than another. I always say hydrogens love hydrogens. So these three hydrogens together are very strong, and it's much more difficult to take the hydrogen from this side. These two hydrogens together are not so strong, and so it's a little bit easier to take one of these hydrogens from the two. So this yellow one is the major product, and this purple one is the minor product. And again, that's a lot. Major is about 90%, more than 90%. So that's been a lot of reactions for alcohol. Alcohols can do a lot of things. They can also do what's called a condensation reaction, but this is the main reaction for organic acids. So I'm going to leave that for now, and so we'll see it later when we learn about the organic acids and their reactions. Okay, so there's one more little thing. What about these aldehydes and ketones? Well, we've already seen one of the reactions of aldehydes and ketones. They can both undergo reduction reaction. So aldehydes can undergo reduction reaction, and ketones can also undergo reduction reaction that we saw earlier. It's one of the ways of making an alcohol. Now, for aldehydes, there's one more reaction that it can do, and actually we saw this earlier as well. We saw this as the second reaction with primary alcohols. So why do I have this in this section again? Well, to remind you, and a lot of this we do see connections between one type of compound and another, but there is a slight difference with aldehydes. The reagents are a little bit. So these first two are actually the same. These oxidizing agents are very strong, so they react with alcohols and they react with aldehydes. These other two are new because they are weaker. So they can't react with alcohols. They can only react with aldehydes. And so this oxidation reaction, again, is very, very useful for distinguishing things and identifying things. So we already know the color changes for permanganate and dichromate. Do you remember? For toluenes, it's a cool one because it's actually has a silver ion with ammonia. That would be the chemical formula for Toland's reagent. And so at the first it's colorless and it forms silver. It forms actually silver metal, and often it looks like a silver mirror on the side of the glass. So it's quite a cool one. Benedicts or Fehlings, they're similar, although they're slightly different mixtures, but they both start off as blue because they contain copper 2. And they become red precipitate. They form a red precipitate. The red precipitate is copper 1 oxide, and so it's not soluble in water. So it changed from the blue copper 2 to copper 1 oxide, although it's a mixture. You can't just write copper 2 instead of Benedicts or Fehlings. You do need to write the name. So those are all of the reactions now, so many for alcohols and just a few for aldehydes and ketones. There's lots of practice in your book. We'll do some together and you can ask any questions if you want clarification. See you soon. Bye-bye.